if you listen to two mathematicians talking in an office, one trying to convince the other of a new idea they've come up with, you'll hear words like, do you get what I mean? Do you believe that it's true? Do you think I have the right idea? All right? That doesn't sound like proofs, right? That sounds like two people trying to convince each other of something or trying to get an idea across. And that's how proofs begin. They begin by, does it seem reasonable? Does it seem plausible? Do you believe that this is the right track? The same way somebody who's writing a novel might say, do you think this is a good idea for a book? Okay, but it doesn't make the novel yet. So the novel is only there once you take your idea and you decide what characters are going to be there and what chapters are going to be there, and you actually start putting the paragraphs down and you rewrite it and you rewrite it and you reorganize it. Same with a proof. You think, you finally get the idea, you refine the idea, you check the idea, you look for holes, you plug the holes, and then you say, now for sure I got the idea, then you write it up. And the way you write it up is in English class. Think of the idea you want to say, have a topic sentence, and step by step try to explain in English what your idea is. If it saves you some time in the middle to use a mathematical expression, then use it. Now, this is a little vague, so maybe I should do an example. I was just going to do an example from the homework, which would... the thing I like about my problem set is that every problem, there's a lot of different ways to do it. So if I just go over one, you're going to think, oh, that's the way to do it. And I don't really want to do that. But there are elegant ways of writing proofs, but they don't always have to look the same. Do whatever you think is clear, whatever you think makes sense. So what's a good example of this? It's a good example. I was going to do the one with the ADU ball. Should I do one little proof of ADU ball? How about this? I'll give a wrong proof of ADU ball. And you tell me what's wrong with it. Okay, here's a proof of ADU ball. You're trying to prove that you can get more than 60 with combinations of 7 and 11. Okay, so I start with 61 because I'm experimenting. How can I get 61 equal to a combination of 7s and 11s?
Well, what's the problem? I haven't read it.
You have a game where you can score 7 points or 11 points, and you want to show that some sequence of scores will get you any score 61 and higher. Actually, 60 or higher as well.
3 11s.
So 3 11s, and how many 7s? Let's check that. 28 and 33. That looks good. All right, fine. So I did it for 61. And now all I have to do is do it for 62, 63, and all the other infinite number of integers, and my proof is done. All right, well, that's a bad way to prove it, because we'd all be dead before the proof is over. We need a more general idea, and the hint here is to think inductively. Now, I'm actually going to rip the guts out of this problem the last week of class. We're going to completely analyze it from a number theory point of view. You're going to understand the complete theorem. You're going to understand everything behind it. We're just going to take all the clothes off of this thing. But right now, I just want you to scratch at it, like it's this weird, diamond in the rough you found, and just get some sense about it. So I said, prove that this particular example is true. In the general case, it'll be any two numbers. In the general case, we're going to have a way of calculating exactly what these two numbers are, not just figuring out on the fly. But right now, all we got to do it is for 7 and 11 and prove that you can get any number bigger than 61. So here's my phony proof by induction. Okay? So where's my phony proof by induction? I'll say, well, let's pick any number and let x be a number greater than 61. Okay? Any number bigger. I'm going to handle all these cases at once now. So by induction, I'm going to assume that I can get all the x's lower than this number as combinations of 7 and 11. That'll be my inductive assumption. And I want to show you that I can get x as a combination of 7 or 11. All right? I'm doing this proof by induction. So I'm going to assume that... Jesus. What a noise. I'm going to assume that I can get any number smaller than my x with a combination of 7s and 11s. Well, if I can get any number smaller than my x with a combinations of 7 and 11s, I can certainly get x minus 7. By induction, x minus 7 can be written as a times 7 plus b times 11. By induction, I assumed it because it's a smaller case. Everybody agree? I didn't do anything wrong so far. Hence x equals, and you tell me what x equals. X equals a plus 1 times 7 plus b times 11. So I conclude x can be written as a combination of 7s and 11s. And I picked any arbitrary x to start. What a simple proof, right? It's almost too simple, right? It's too slick.
Your base case is simple.
Right, my base case is wrong. It's a subtle issue here that my base case is wrong. But the point, we'll talk about what's going on with the base case in just a second. But look what this looks like. When I do proofs for you in class, I'm talking, I'm sketching, we have interaction. I rarely will sit here with my back to the camera writing the proof up just like I did here. This is not how I'm going to write proofs in class. If you want to see proofs written like this, go to the book where somebody did that, and then they publish it in a book, and you can read it at your leisure. It's too slow and not useful for me to write proofs like this. All right? I'm going to be talking and filling in stuff in the board as I talk, hoping you're listening. It's faster if I talk and you're listening. But this is a nice way to write it. There's nothing fancy about this. It's just, you know, basic English sentences. Let x be a number bigger than 61. By induction, x minus 7 can be written in this form. Hence, x can be written in this form. Hence, x can be written as a combination of 7s and 11s. End of proof. So where did I go wrong? Well, I didn't have any base case. So let's make a base case. So here's my base case. That's a fine base case, right? Is that a fine base case?
You said x has to be greater than 61.
Oh, well, no, but that's okay. I want to show that it's true for 61 and higher, Doug. So here's my 61 case, my base case. And now here's my proof that I can get anything bigger than 61. So that's not a problem. That's okay. What?
You would be able to get 62.
Right. Think about how you get 62. If I went through my argument, I would take 7 away. And where does that end up?
55.
Right. So there's some subtlety with induction. You need a base case, but you need a base case that you'd sooner or later end up at. You don't want to skip over or pass your base case. Otherwise, this nice little link of reasoning passes right over the point that anchors you. Okay? It's like jumping and missing the trampoline. Ouch. Yes, Seth?
By induction, x minus 7 can be written as a times 7 plus b times 11. I don't see how we proved that.
We didn't. That's an assumption. The idea of induction is that we're not proving the induction assumption. We're assuming it's true, and we're going to prove how to get from there to the higher case. And as long as we have a place to start, we can repeat that argument and get all the cases. So we didn't prove this was true. It's by induction. We assume it's true.
If you prove that x can be written as a times 7 plus b times 11,
then we'd be done.
then it's a valid inductive step or whatever.
No, this step is valid just because it's a smaller case than what I started with. If you're trying to prove something by induction, you can assume for free. It's like you all wrote recursive programs for a whole month, right? How do you know your recursive programs work? It's because when you call the program again on the smaller case, you assume that ends up working. Right? Why does that end up working for you? Because sooner or later you have this base case that bottoms it out and it comes running up the stack. Right? So I'm trying to write a program to show you that I can write x as a combination of these two things. I recursively assume that I can write x minus 7. Think of this as a recursive call. I get it for free, just like you get your leap of faith in recursion for free. I'm appealing to what you know from programming to maybe give you a sense about this. But this comes for free. You don't have to prove that.
This is a base case for any number of the form 61 plus 7x. Or
That's true.
61 plus 11x.
That's true.
You've covered
So-
some of the cases.
Right, so you've covered some of the cases. The way you can cover all the cases is you need 7. You need a sequence of 7 base cases. So that means you can't jump over it. If you're taking away 7, you got to land inside that big trampoline of a base case. So the size of your base case has to change depending on your argument. There's a lot of subtleties in induction. And I gave you a bunch of problems in about a week or two where we talked just about induction for a whole day. And you'll discover a lot of these subtleties as you go along. And you'll discover them in this problem set too.
Which part are we calling the base case here?
This is the base case, 61. This is the inductive assumption because it's a case that's smaller than the one I started with.
The reason it doesn't work is because we're making jumps of 7 every time instead of jumps of 1.
Yes, that's exactly why it doesn't work. Because in my argument, if you check, the actual inductive argument is fine, but the base case isn't big enough to catch it. So as you go down by jumps of 7, you would actually pass the base case by, and it wouldn't really work. Or the way Sam looked at it, this is true for anything that's 61 plus multiples of 7. And that's not all the numbers. That's just some set of the numbers. All right, so this was meant to be a little review about how to write a proof and how to ask yourself whether you've written it. If your gut instinct is, oh, I know it's true, but I just don't know how to explain it, then you got a long way to go. Okay, but if you really, really know it's true and you can explain it to somebody and you're able and you're really positive you got it and you can convince somebody. Not the kind of convincing, I want you to go to the movies with me and you want to stay home. The kind of convincing that you're working together and you found the truth. If you've gotten to that point, then just go back to English class and write your idea down in English. And you'll nail it down. All right? Now, the real idea of a proof is sociological. A proof in a journal is as rigorous and strong as the professional mathematicians who looked at that proof and checked it. And there are many famous examples of proofs that got past referees into journals of famous theorems that 30 years later, another famous paper says, oh, gee, this theorem was wrong. There's a mistake in the proof of this. And then somebody had to either fill up the hole or actually maybe not fill up the hole. One of the famous examples of this is, anybody hear of the Four-Color Theorem? There's that if you have a planar graph, you can color the vertices with 4 different colors so that every 2 adjacent vertices have different colors. Or if you have a picture of the United States, you can color it with 4 colors. No 2 adjacent states have the same color. That theorem's true. It was actually proved for real in the mid-70s with the use of a computer in a very, very controversial proof where you couldn't really verify the proof unless you trusted the computer's calculations. So it got the philosophers talking a lot, and the mathematicians weren't really satisfied because it wasn't much of an elegant proof. But there was a beautiful, elegant proof of this back in the 1800s, which was in the journal for 15 years before somebody else published a flaw in the proof. So people thought it was proved, found a flaw, and the good thing about the proof is that it still managed to prove that you could do it with 5 colors. But it wasn't strong enough, the hole wasn't pluggable to make it work for 4. And it remained as an open question whether you actually could do it with 4 all the time, all the way up until the mid-70s. And then 2 guys from the University of Illinois proved it then. All right, so it gives you an idea. What's a real proof? It's what really is true. What's really true? Turn it all into logic, step by step by step, so no human in the world could conceivably figure out what it means. Right? That's not good enough. It's got to be a balance. It's got to be a balance between rigor and intuition. And our class has our own standard of that.
Humans have double-checked the proof of the computer?
I don't think that they've actually double-checked each of the steps. I don't think that's actually been done.
No human being has gotten to the end.
Right. Although you can write programs that check the integrity of the program. I mean, it's a philosophical issue. I mean, what if that machine just had a glitch? So here's what happens. You get a paper, some editor that gets a paper on a particular subject. Say I've published a paper on that subject before. And they say, would you mind reviewing this paper? Then they send you the paper, and then you spend hours and hours, depending on how sincere you are, really trying to figure out what this person is saying. And sometimes it's very difficult. Sometimes because they didn't write it well, sometimes because it's just difficult material. You go through it, you check if it's correct, you check if it's interesting, all sorts of things, but mainly for correct and comparing it against the current literature, because presumably the person reviewing it is an expert. And then you give an opinion. This is no good, it's been done before. This is no good, it's wrong. This is good, but it needs to be rewritten. This is good, it's pretty good as it is. This is good, perfect. And you give an opinion back to the editor, who then communicates it to the person who wrote it. And there's usually 2 or 3 or 4, depending on how serious the journal is, referees for each article. So look, if you're really, really busy trying to get tenure and writing your own papers and getting your own grants, and suddenly you get this and it takes 15 hours to do this during your week, and you say, oh, well, this semester I refereed 6 papers, no tenure committee cares that you refereed 6 papers. They'll say they care.
They do care if you're an editor of that journal.
If you're the editor, they might care, but the editor does a lot of the passing stuff back and forth, and not so much of the. This is just stupid politics. This has nothing to do with.
You're debasing these pure mathematicians.
All right, let's get back to where we were. Okay, I finished up last time showing you that you could take any Boolean formula that you can represent with a truth table and put it in terms of ands, ors, or nots. So Chris Crick, where is he? He asks, can you do it with just ands and ors?
Ands and nots.
Ands and nots. Can you do it with ors and nots? Can you do it with ands and ors? Some of you had an idea. We were doing it right on the spot. I said, think about it. Is there any consensus? Can you do it with ands and ors?
Ands and nuts, yes. And then nuts.
Ands and knots, you can do it. Because A or B, how do you write A or B in terms of ands and knots? Then I'll believe you. Push that not through and double check this. Not A is A. Flips this to or. Not B is B. This is an identity. You could prove it with a truth formula. You could prove it with our manipulations. Because you can convert every A or B into this form, then any place you see an or operation in a formula, you could replace it with ands and nots. So it's true. Ands and nots are a complete set. In fact, everything is symmetric in Boolean algebra. So ors and nots are a complete set. And this identity is true. Right? You can always flip nots and ors and ands, and everything always stays true in Boolean algebra. That's also true. So ors and nots are a complete set. What about ands and ors? What do you guess about that? You can have a hard time getting a not gate or getting a not just out of ands and ors. But I'll tell you a really cool computer architecture problem. What if somebody gives you one not gate and all the ands and ors you want? Can you simulate more than one not gate? If they give you two not gates, two not symbols, you can only use two of these, two minus signs, and all the ands and ors you want, can you create more not gates? So it turns out you can. It's a very difficult problem, and it's really tricky, and it's a cool puzzle, but it belongs in the architecture, how computers work course, not really in this course so much. Anyhow, moving on. The method we used last time to come up with a formula with ands, ors, and nots creates something in this kind of a form. Something like this. This was the example we did last time. This kind of a form always comes out of a truth table. Sometimes you have nots on the variable, sometimes you don't. You combine them together with ands because you want the whole row to have those 0 and 1 values. And then you connect them with ors because you want either this row or that row. This kind of form has a name. It's called disjunctive normal form. It's a fancy name. What it means is, disjunctive basically means ors. You or together collections of things which are anded together. Right? What's more, every single Boolean formula has a unique disjunctive normal form at some kind of a level. I won't get into too much of it, but you can always write it in disjunctive normal form. There's a flip side of this. Instead of taking things that are multiplied together and adding them, you can take things that are added together and multiply them. All right, so in this case, well, let's not do this case, but I'll just put any example up here. This is an example of the other kind of form. This is conjunctive normal form. Things connected with ors, and then they're multiplied together. They're duals of one another. Here where you see addition, there's multiplication. Here where you see addition, there's multiplication back here. Okay, so this is conjunctive normal form. This is disjunctive normal form. They're both useful for different kinds of things. There's a problem set that asks you to use the same method I did to come up with this kind of form. And that's what Sam was saying the other day. He said concentrate on the zeros and push a double not through. I'll let you work on it on the problem set. But you can always come up with a conjunctive normal form and a disjunctive normal form for any formula. All right. Peter? No, they're not the same. They're not the same. These are just showing you a conjunctive normal form.
What makes the first one disjunctive is the fact that it's some blob with a...
Some blobs of multiplied things connected by ors. Yes.
And the other one is some blob connected by an and.
Right. So these are things ANDed together which are then ORed. These are things ORed together which are then ANDed.
So does that, in the first case, it has to be things that are ANDed together? I mean, we couldn't have some things within a parentheses with
That are ordered together. That would be in the normal form.
That's not in any normal form.
what defines a normal form?
It's got to be things multiplied connected by ORs to be disjunctive normal form. This is not things multiplied strictly connected by ORs. Here's the OR. That's okay. But that's not okay because this is not a single variable. That's got a plus in it. So this is too complicated to be considered in either normal form. And it's a very common thing in math to take stuff that can look in an arbitrary way and use the fact that we can always make it look in a particular way. Because we can always say, okay, make it look in this particular way because now my argument's easier. So the two particular ways people generally use for Boolean formulas are conjunctive normal form and disjunctive normal form. And you'll see this later because it's going to come up in a computer science idea in 20 minutes.
A single variable.
Single variable is okay. Yeah. Right. Think of that as like W times true. Right.
If you just distribute it, then it would be disjunctive.
Right, exactly. Good, Anthony. Right. If you distribute this out, then it would be in disjunctive normal form. Right? You get R times R plus R times W bar plus W. And that would be disjunctive normal form. Good, right. And you can always do that. You can always manipulate it and get it into one of these forms. All right, questions? So we talked about these complete sets of operators, and an OR, and a not as a complete set, or not as a complete set, and an OR is not a complete set. Are there any Boolean functions that are complete all on their own? And the answer is yes. All right, so one example is an operator called NOR. And here's the NOR operator. Sometimes it's written like this. NOR is the same as not OR. So this is the same as let's fill in the chart. What's the values for the NOR function? One, 0, 0. These two are the same. You sure that's right? Let's check it. 0 or 0 is 0. A not sign in front turns it to 1. 0 or 1 is 1. A not sign in front turns it to 0. That's going to be the same. What about 1 or 1? 1 and 1 is going to be 1, and then not sign is going to make it 0. Right, that's the NOR function. It turns out that the NOR function alone can get you any other function you want. You can combine NOR things together. And I'm going to prove it to you. And it's a really, really straightforward proof. I'm going to prove to you that I can get not by using NOR, that I can get and by using NOR, and I can get or by using NOR.
Well, you can stop after the first two, though.
That's true. I could, based on Chris's comment, and that's true. So let me show you how you get not. Check this yourself. If I took a variable and I NOR it with itself, what happens to it? If it's 0, it ends up being 1. And if it's 1, it ends up being 0. So x NOR x is the same as not x. Every place you see a not x in a formula, you can replace it with x NOR x. So that gets rid of all the nots in your formula. What else might happen? You might have an x or y. It turns out that this is equivalent. This is a little harder to run and check through, but you can do it. Let's try a couple cases. 0 or 0 should be 0. Put 0, 0, 0, 0 into here and see what you get. 0 NOR 0 gives you 1. 0 NOR 0 gives you 1. 1 NOR 1 gives you 0. So it agrees. You'd have to check all the possibilities to make sure that these two are identical. Make a whole truth table and double check it. You can also do the AND. I'm going to put down the AND because it's so nicely symmetrical and it'll help you on the problem set when I ask you to do this with a different gate. that turns out to be equivalent to x and y.
No.
Here I have 2x's, 2y's. Here I have xy, xy. It's very dualish. Is it right?
Yeah, right?
You checked it?
They're backwards.
It could be. Well, we can check it. Let's check.
Yeah. So what happens if you have 1 and 0 on the top?
And here?
Yeah.
I could have made a mistake. Let's check. 1 and 0. So that means this is going to be 1 nor 1, which is 0. 0 nor 0, which is 1. And then 0 nor 1, which is 0. So that's not right, right? These are backwards?
Yeah.
I got them reversed?
Yeah, your note sheet shows it reversed too. Lecture.
Oh, I wrote them?
I wrote them correctly in the notes.
And the notes are right and this is wrong. Yeah, great. You know, the funny thing about this is that when I first wrote these notes, I made the mistake in my notes. I corrected my notes. I do this lecture now. I'm thinking, oh, crap, did I correct them incorrectly? And I didn't. I corrected them correctedly and then copied it wrong. This is correct. All right, let me show you how to use this. How would you take any formula at all and use this information? Let's say we have P or Q and not P. Let's say we wanted to take this expression written with ands, ors, and nots and turn it into something that just had nors in it. We're just going to work our way out from the inside out. And you could actually write a program to do this. I didn't force you to, but you can. Let's turn the not first. Okay, so P not ends up being P nor P. Now I've got P or Q. Let's do that. P nor Q, nor P nor Q. Good. Yes?
What's the symbol in
Oh, it's just an arrow written the wrong way. Sorry. I was standing on my head for a moment. We still have an AND gate left, right? Or an AND operation. I keep saying gates because I'm going to do an example in circuits in a minute. How do we get rid of this? We have to use this expression. But now the x is all of this, and the y is all of this. This is ugly. Ugh. But I'll do it. There. This formula with just nors in it is equivalent to that teeny formula there. All right. Is it the smallest formula with nors in it that's equivalent to this? No. You can probably do better. Okay? It's just a way of showing that you can always do it, but you can probably do better. And the issues of doing better are more complicated. But
you could reduce the original formula to Q not P.
We could even start with easier stuff, true. But even with this can definitely be reduced a lot. Let me tell you something about why people care about complete operators. If you go and think about circuits, you can buy circuits that do all these different operations. Here's an AND circuit, or an AND gate. Two things come in, one thing comes out. AND. Electricity goes into this little box. Electricity comes out. 0 is a low voltage, 1 is a high voltage. Two high voltages come in, high voltage comes out. Anything else comes in, low voltage comes out. It's just a physical analog to what we've been talking about. You build computers out of things like this. Now what's inside things like this? Well, it depends what decade and century you're talking about. If you go back to 2000 BC, you can build these things with streams of water running through and big holes in the ground, streams of water running in, and when somebody puts input in, they take a big rock, that's one, and they cover the hole, right? So if you have the stream of water with two consecutive holes in it, then if two people cover the holes, then the stream of water will run through. Two ones come in, two big rocks come in, the stream of water comes through, right? If anybody doesn't cover their rock, their hole with their rock, then the stream of water goes down the hole and it doesn't come out the other end. So you could build an AND gate out of streams of water and big rocks and holes in the ground. And if you built a computer, the scale of that size, it would be, maybe the city of Cambridge. And then there's a timing issue, making sure everybody is running with their rocks and covering things at the right time. And that's why nobody built a computer 4,000 years ago, because the technology's got to catch up with the idea. All right, so if you're let's jump up to the 1940s. All right, then you get what's the 1940s? Vacuum tubes, maybe. 1950s vacuum tubes. 1960s, transistors were invented. Right? When were transistors invented? 1961. Somebody won us a Nobel Prize for transistors, right? It's a huge invention. It's a big thing. Transistors basically allowed these things to happen with much less heat, much smaller, much faster. And nowadays the technology improves and improves and improves every single year. They get better and better. You know how much time it takes for electricity now to get through an AND gate? Something on the order of a billionth of a second nowadays. A nanosecond. 1 billion times you can go through these gates in a second. And 4,000 years ago, it took about 5 minutes for people to move the rock and get through the gate. So it's on the order of, 15 orders of magnitude faster today. All right. Which gate is actually the fastest? I didn't tell you how you build these things. You put transistors inside them. You use VLSI. You use all sorts of electrical engineering stuff, which you don't need to know about. But inside is a black box. It does what an AND gate's supposed to do. But you should realize that if you go to the store, the fastest one of all these gates is actually a gate called the NAND gate, which stands for not AND. It turns out that you can build this with the minimum number of transistors. And if you time how long it takes the electricity to get through a not AND gate, it takes the fastest. So you'd love to be able to build everything with just these gates, because then you'd get the least delay through your circuit. This is real electrical engineering idea, not so much a computer science idea, but it relates. It turns out a NAND gate is also a complete circuit, just like a NOR gate is. But it turns out, electrically speaking, it's a very fast one. So there's a trade-off, because if you turn everything in terms of NAND gates and then you get a ton of NAND gates, even though they're fast, what good is that? So there's all sorts of issues here. Theoretical issues and engineering design issues, and you'll see it in computer architecture and how computers work. All right, questions about this?
What does a NAND gate do?
It's a not AND. The same way a NOR is a not OR, a NAND gate is a not AND. So it would be 1110. That would be a NAND gate. There's 3 big applications of computer logic that I want to talk about. One has to do with algorithms and with this idea of a reduction. One has to do with computer architecture and the idea of building a circuit. And one has to do with AI and the idea of theorem proving. All right, I'm going to try, to get through all of these today. Which is the best one to start with? So I'm going to do circuits first, because we were talking about it, and everybody's freshly thinking about circuits. Here we go. We're going to talk about how you can take stuff from an electronic catalog, buy some of these gates, and build something that does arithmetic. Right? It's not exactly a computer yet, but at least it's getting there. Computers do a lot of arithmetic. So in order to do this, we need a little bit of an introduction, not too much. We need an introduction to binary numbers. Binary numbers are numbers that are just zeros and ones. And you can represent any number in the whole world with binary numbers. Quick intro. With normal numbers, you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You run out of symbols. 10. Right? There is no T for 10. So what do you do for 10? You put 1 in this column, and then you put a 0 here. This is so ingrained in our heads that we never think about it anymore, right? 1 is in the tens column, 0 is in the ones column, that's 10. If it's so ingrained in your head and you get it, just do the same thing for binary numbers. Let's count in binary. I took away all your symbols except for 0, 1. When you get to 1, you're done. 0, 1. You're out of symbols. What do you do? Now you can go 1, 1, right? This is like 99. You're out of symbols. 1, 0, 1. Out of symbols. 1, 1, 0. 1, 1, 1. Out of symbols again. Okay, your numbers get pretty long faster than they did before, but it's a perfectly fine number system. How do you add binary numbers? Well, the really goofy way is to take the number, convert it back to base 10, add in base 10, and then convert it back to binary. It's like, well, you don't have to do that. You can just add them straight. Look, what number 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 is 1. This is the number 3. This is the number 4. 3 and 4 is 7. Right? The same arithmetic algorithm you used to use works for binary. Who's still with me? Easy? Okay. I didn't do any carrying here. Let's do some carrying. 1 plus 0 is 1. 1 plus 1 is 0. Carry 1. 1 plus 1 is 0. Carry 1. And that's also right. This is the number 3. This is the number 6. This is the number 9. Okay? This is the 1's column, the 2's column, the 4's column, and the 8's column. Instead of having a 10's column and a 100's column and a 1,000th column going up by 10 each time, we go up by a factor of 2 each time. Right? Yeah, Brian?
If you were adding 3 numbers this way, you had to carry a 2 across. Would you distribute that one at a time over the columns?
Computers don't do that. They add 2 numbers at a time, and then they add the third one to the sum of those 2. And you would never design a circuit. Well, I shouldn't say never, but they don't do it that way, and specifically because of what you're implying with your question. Yeah. Yeah, Donna.
0 in the left-hand column of your upper number, is that just like a placeholder, so it looks like 3?
Yeah, yeah. I didn't have to put it there, right? Because the truth is, what you really do there's the next step. Say you wanted to build a little machine that does addition. You have to decide how big your numbers are. So typically in a computer nowadays, the numbers are 32 zeros and 1s long. If you have a number bigger than that, you have to come up with a better way to do it. In fact, in Scheme, you see how you guys can do arithmetic in Scheme? If you do 100 factorial, that's way bigger than what the computer can store. The computer doesn't actually do arithmetic on the circuit there. It actually splits the number up into pieces, puts it in a list, reconstructs it. It actually stores it in lots of different numbers. It does it in a different way. But if you want to store just one number, it's typically 32 zeros and 1s long. So here's what an addition circuit might look like. 32 zeros and 1s come in here. 32 zeros and 1s come in here. And out comes how many zeros and 1s? 33, because there could be a carry. Right? But if you're building a computer where every number has 32 zeros and 1s and they go around wires, that are 32 in parallel, like Red Rover holding hands, what do you do with a number that comes out 33 bits? It doesn't fit on the highway. Okay, so actually, this extra bit has to go someplace else. So I'm going to write it like this: 32, and then 1 comes out here, goes somewhere else, and you do the appropriate thing with it. What's inside something like this? Well, I'm not going to go too much into this, because that's really for next month. But I will explain to you how we can focus and build precisely, and we'll do it in the next 10 minutes, a little circuit that's just one column of this. We would need 32 of these circuits connected together with the carries sent to the next one on its left. And we can put all those 32 inside here, and we'd have this circuit. But I'm going to show you just how to build one for one column of this addition. We would need 32 copies to really do it. And what's more, just to make it easy, I'm not even going to deal with a carry. I'm just going to assume, well, you'll see. I will deal with a carry, but I'm not going to connect it. I'm just going to show you one column. Let's do it. This little circuit I'm building is called a half adder. And like any circuit or any Boolean function, it can be represented in a truth table. 2 things come in. The bit from one number and the bit from the other number. And one thing comes out called the result, and one thing comes out called the carry. I have 4 possibilities for the things that can come in. If I add 0 and 0 together, the result is 0, and I carry 0. If I add 0 and 1, the result is 1, and I carry. If I add 1 and 0, the result is 1, and I carry 0. And if I add 1 and 1, the result is 0, and I carry 1. Okay? Each of these is a separate function. I got the carry, I got the result. We're going to design each of these separately. Let's go ahead and write a formula that actually gets these. One of them should scream at you because it's just a basic one. Which one of these is easier? Well, actually, they're both kind of easy. The carry is really straightforward, right? What's carry? It's and, right? So carry equals x and y. Okay? What about result? X what? X exclusive or Y. Okay, so we wrote exclusive or in a lot of different ways. Let's write it with just ands and ors and nots. How would we do that? Remember our trick? We'd say not X and Y, or X and not Y. Right, same thing. So let's do not X and Y, or X and not Y. That's exclusive or, and that represents the result.
And the symbol is a plus with an or on it?
A plus is an or.
No, the symbol for the...
Oh, it's a plus with a circle around it.
And why would we just write it in terms of the XOR symbol?
No reason.
Okay.
Good question. Right, the reason we're not is because the only gates we have are these ands and ors and nots. And we're going to make a picture with ands and ors and nots, and you'll see it in a second. So here's our circuit. Here it is. The way you write a circuit is you put a little box here. You put the inputs on the top, the X and the Y. I put little arrows so everybody remembers what direction things are going. The electricity is moving in a certain direction. Usually you don't see arrows in books. You just get it from the context, but it's easier to see it. There are two things that come out of here. The result and the carry. Why did I put the carry coming out the side? Because, like I said, you're going to have 32 of these circuits next to each other, and this carry should probably go into the next one so it can pass its result on. But right now, let's just concentrate on this circuit. How do we do it? The carry is the easy part. It's just an AND gate. Here's what an AND gate looks like. Here's X. So here's Y. Here's X. There's some conventions here. If in a circuit you see a black dot like I'm trying to make here, like a little, that means you just spliced a little wire off of here. You just took it and you sent it over here. I sent the Y over here. The reason I made those little dots is because I'm going to have to take those X's and Y's and send them down to another part of the circuit in just a moment. So I just splice it off.
Is the AND gate just a curved end and a straight back?
It's a straight back here and a curved bottom. That's an AND gate. Every AND gate looks like that conventionally. A D upside, a D rotated, yeah. Okay. By the way, sometimes it's hard to draw these pictures without crossing lines. If the lines cross, the implication is that when you actually build the circuit, you don't let the lines cross because you'll get a horrible short circuit and things won't do right. So you raise them above or below one another. If you see a black dot, that means they really do connect. Okay, so anytime they cross without the black dot, they're not connected. Now we need to do this. It's a little harder. The way to do it is I just like to build it from the bottom up. So the last thing that happens is this OR. So an OR is going to go into the result. Here's what an OR gate looks like. It's kind of got a pointed bottom and a curvy top. Two things are going to go into this OR gate. This piece and this piece. We have to construct those two things. We need not X and Y. So let's get not X and Y. Here's not X. I'll pull it down here. Here's a not gate. There's a little triangle with a bubble on the end of it. That's not X. And here's Y. That's not X and Y. Not X comes this way, Y comes this way. They go through an AND gate. Not X and Y comes down into the OR. Now I got to do this part, X and not Y. So here's X coming into an AND gate. Here's not Y coming down from here through a bubble and then into the OR gate. Yes?
Just to follow up on my last question, is the reason we don't use a specific XOR gate just that it's faster to shoot it through the combination of the ANDs or something?
No, it's not. And actually, if you went to the store and bought an XOR gate, we would just have one little gate here with an XOR marked on it.
Okay,
It's just because you always, At the beginning, you always build circuits showing ands and ors or nots. That's a convention. And you could do it another way, and there is no good reason.
Okay.
Yeah. All right, let's look at this. Are there questions about how I constructed it? Here's what I expect you to get out of this. You should be able to take a truth table, construct the formulas. You should be able to take the formulas and make that picture. Okay, working your way backwards. Once you see the picture, that's it. You can give this to an engineer and they can build it. And it's something that does arithmetic with electronics based on theoretical logic from the 1880s. Now tell me, how long does it take to get through this circuit if every single gate you see takes 1/billionth of a second? You want to understand that question? Computers take a certain amount of time to run. What slows them down? What slows them down is how many gates they have to go through before something interesting happens. So let's see. To get out the carry, it only takes 1/billionth of a second. But here's 1, here's 2, here's 3. There's a depth of 3. You can think of this as a tree or as a graph. And knowing the depth of the graph is important. That's why people study graph theory. It connects in figuring out how fast these circuits are going. Actually, you can see that this particular idea of a circuit is really cruddy. Because how do you really do this circuit? Like I said, you have another one just like it over here, right? And you pass this carry over there. And that's going to take another 3 to get this out. And if you have 32 of these, then it's like 96, right? There's no ALU, there's no arithmetic logic unit that is sold today that uses this idea. Because it's just way too slow. They use better ideas. And that's what you talk about in how computers work. You talk about how to build better ALUs. You talk about how to build better pieces of a computer. There's something else that's a little wrong with my generalization. How would I send this carry over here when this thing only takes 2 things? Right? I go back to my engineer and I go, Dumkopf, right? I say, you dope. How am I going to take 32 of these? I need an extra arrow coming in, right? So I need an X, I need a Y, and I need a carry in. Call this carry out. I need a carry in. What would the carry in be here? Right, the one here on the right end would always get a 0, but all these would really get something. Connect it.
So wouldn't you have to redo?
Yeah, you got to redo everything. This circuit is called a full adder. It's not a half adder. It's different. It's something that really does something useful. This is just when you're teaching people to get them used to the idea, and then you say, oh, it doesn't really work, and then you say, now do a full adder. All right, so this is called a half adder. A full adder has 3 inputs. How many rows are going to be in the table for a full adder with 3 inputs? 8. You got all of these. You got to put a 0 in front of all of them, and then you got to put a 1 in front of all of them. So it doubles. You're going to get 8. It's a bigger circuit. It's more difficult. All right? We're not going to do that now. We're stopping here now with circuits.
You had said that we need to be able to produce this diagram with half-adder circuits, but then you
Not this ugly one. Something prettier.
Okay, yeah, because actually in all those lines and whatnot, I couldn't quite make out what was going on.
That's because I'm about the worst person to draw circuits. I hate doing it, and I'm not good at it. But I'll show you what's going on.
Okay.
It comes down from here. It splits this way, and it splits this way, and it splits this way. It splits 3 ways. Into the NOT gate, into this AND gate, into this AND gate. This Y also splits 3 ways. Once directly into this AND gate, and then down here into this AND gate and into this NOT gate. Any place where you see a cross and there's no big black circle, then there's no connection. If there is a big black circle, then there is a connection. So there's only 3 black circles on my picture, 1, 2, 3, and all the other crosses are really going over or under. Does that make better sense now, Tony? Okay. That's a good point. I was trying to gloss over my ugly picture, but it's right there. Other questions? Who gets this? Everybody get it? Yeah? Makes sense? All right, good. Good. By the way, I should mention it, but I won't go into the details. The way computers do addition is just this way, more or less. The way they do subtraction is also this way. They use the same circuit to do subtraction as they do to do addition. And they use a method that you're not used to in school, because in school they teach you to borrow when you do subtraction, and they teach you to regroup when you do addition. but you could actually do subtraction through an addition algorithm if they bothered to teach you it that way. And it turns out that that way is much more natural for machines. What machines do when they do subtraction is they switch all the zeros to ones and all the ones to 0, and they have this carry in end up being a 1 for subtraction. And it turns out to be the exact same circuit will do subtraction that used to do addition. And there's some, that would take you about 15 minutes to really understand if I had time to do it now. But you'll see it in how computers work. And the idea is to represent numbers in what's called 2's complement form. Sometimes special ed teachers use this for kids who have real trouble figuring out subtraction somehow, but were really good at addition. And they just say, well, here, just learn how to do the complement idea, and then you can just do addition again. And maybe it works, maybe it doesn't, but something for education people to think about. In the notes, I did another example of a circuit, which I'm gonna beg off now. You can look at it in the notes. I did an example of what's called a threshold circuit. Some people who do neuroscience or who do AI like to try to represent what brains do. Some do it in a way that represents the output of a brain, like writing a program that plays really good chess, even though what they do inside is nothing like the way chess players do things. Some like to go right to the heart of things and let's just represent neurons and see what happens. So more or less the way neurons work is that they get things firing into them, and every neuron has a different threshold, and when it gets a certain number of things that fired in, it fires something out. And that completely simple idea somehow makes us have consciousness and various other incredibly high level, and nobody knows, has any idea how it works. I mean, they know a little bit, but not all that much about how the brain works. So one cool thing to do is experiment. We can build circuits that act like that. We can build a circuit that has 3 inputs and that fires anytime it gets 2 or more in things. You can look at a circuit. I did it right here on the paper. You can build a circuit that has 10 inputs and it fires every time 7 or more come in. And you can connect these up and let them run in a lab and see if they do anything clever. Well, you can kind of program these things to do things that are clever. Like one thing that humans can do that computers can't do very well, that you all can do, is distinguish faces. Right? I mean, I can tell 98% of the time glancing at somebody whether they're a man or a woman. Even my 3-year-old can usually do that. It's a very complicated skill. Try to build a machine to do that. The machine can get fooled so easily. Build a machine to do it and just put somebody with long hair in front of the machine. And they'll probably mess up. If you actually take it like you guys did at the beginning of the semester, like shave your hair off, forget it. And what about actually recognizing the same person? You know, so you put EJ in front of the machine and you say, this is EJ in August, and now here's EJ in October, and the machine's supposed to know that's EJ instead of somebody else. The machine has a hard time doing this. But actually, if you build like a neural net and you let the thing run and run and run and run, you can kind of train it to recognize patterns. And sometimes it works, sometimes it doesn't. One of the main things you do in algorithms is something called a reduction. It's a way of transferring the difficulty of one problem to another that you're more familiar with. The best way that you can understand the idea of reduction is from this silly joke that I found from the Funny Book of Jokes and Riddles, a children's book. I even gave you the ISBN so you can order it off Amazon.com. The question is, what do you feed a blue elephant for breakfast? Answer, blue elephant toasties. Question, what do you feed a pink elephant for breakfast? Answer, you tell the pink elephant not to breathe until he turns blue, then you feed him blue elephant toasties. So I'm reading this book with my kids and I go, well, that's great. That's just what a reduction is. The idea is you know how to solve one problem, so instead of solving another problem, you fix it a little bit, you do something simple to it, so it looks like a problem that you know how to solve. And then you just use what you know how to do. So it seems when I tell you it that way, that reductions are used to solve problems, to make them easier. And that can be the case. But reductions are also sometimes used to show that a problem is difficult. All right, so let me show you what I mean. Let's say I have a problem A. Here's a symbol. This means reduces to. I'll show you why I use the less than or equal symbol. Let's say I have a problem A and I reduce it to B. In this problem, the pink elephant problem is reduced to the blue elephant problem. Okay? So that means if I can solve the blue elephant problem, I can solve the pink elephant problem. All right, so we would say that this problem, the pink elephant problem, therefore, is no harder or less than or equal than the blue elephant problem. Okay, it's no worse. All right. If you do a reduction like this, you can show things become easier. You can also show things become harder. So I want to do two real-life examples. Here's a problem called satisfiability. It's a problem that comes right from logic. I'm going to give you an example of satisfiability and explain to you the problem. Somebody gives you a Boolean formula. It's in conjunctive normal form. It looks something like this. The OR pieces are parenthesized, and each of these are ANDed together. I write them one under the other so I don't have to go lengthwise. This is conjunctive normal form. ANDs of ORs. You're given a formula like this, and you're asked, can you come up with true and false values for the variables x, y, z, w, and v to make this whole formula true? In this example, the answer is easy. Can you do it or not? It's easy to do it. X can be true, W can be true, V can be true. I don't give a hoot about Y or the other ones. It's really easy to make this true. This has to be true, this has to be true, and this has to be true. So make one of these true, make one of these true, make one of those true. You can't always do this. I could have made the dependencies more complicated. I could have not introduced so many variables. The question that we're dealing with is, given a formula like this, is there a way to assign true and false values to the variables to make the formula true, or is there no way? Okay, that's the question. Let's try to solve this problem and see what our algorithm is. And then I'll talk about reductions. All right, let's really solve the problem. I give it to you for a homework and scheme. How would you solve it? Okay, well, let's assume for a second. In this case, we've got, how many variables here? X, Y, what else? Z, W, V. And here I put my formula. I got a lot of rows. How many rows do I have? Every time I add a variable, I double the rows. Right? So with two variables, I got 4. 3 variables, 8. 4 variables, 16. 5 variables, 32. 32 rows. Right? How do I decide if this formula is going to be true? I have to decide. It's a lot of possibilities here, right? How many possibilities are there? $32, right? I got to check all possible 32. If one of them works, I say yes, the formula can be true. If none of them work, I say no, it can't be. Well, that's fine. 32. I could write a program to do that. It wouldn't take that long. After all, the computer does billions of things a second. So that's fine. What if I do another problem, but this problem has 200 variables in it? Right? How many steps is it going to take? On the order of 2 to the 200. And that doesn't include the time it takes to actually take these true and false variables and put them into here. I mean, that takes some amount of time. Let's call the length of this formula m, and the number of variables n. Then the amount of time this takes is 2 to the n, 2 to the number of variables, times as much time as it takes to run through here and put the true and falses in, times m. All right, the times m doesn't really kill it so bad, but the 2 to the n is death. 2 to the 200th is a huge number. It takes centuries to run that. Way, way too big. So this algorithm, right, in the Ars Digita way, this algorithm sucks, right? We're not afraid to use the word. I'm sorry. It really does suck. This algorithm's no good. It's a bad algorithm. It's too slow. It's exponential. You would never implement it. It would never work. Not in anything reasonable, right? So you need something better. So you get your best programming team and you send them, to work. And get a better way of doing this. This is too slow. And they work and work and work and work, and they can't come up with anything better. And they sit down and they say, boss, we tried for 4 months and we can't come up with anything better. And you yell at them. And you say, try again. So finally, somebody comes back and says, I've proved I can't do it any better. Nobody in the world ever can. And you go, wow, show me the proof. And wouldn't that be cool if they could prove that? How would you prove that? You'd have to prove that any algorithm that they tried would never be better than 2 to the n. How do you quantify over the infinite number of possible algorithms? Well, there are kind of places in theory of computation where you can do this, but for the most part that is hard to do. And nobody has any proof that you can't do better. This is a completely open question whether you can do better or not. Maybe you can, maybe you can't. But say the top 10,000 people in the last 50 years have worked on this problem and have come up with nothing. You kind of figure that unless you're a complete egomaniac, you're not going to come up with something that 10,000 people who are probably as smart as you have worked on for hours and hours and hours. It's probably too hard. It doesn't mean it's impossible, and you might come up with it. Otherwise, Andrew Wiles wouldn't have proved Fermat's last theorem, right? I mean, it was open for 500 years. Somebody's got to do it. But here, nobody's done it, and everybody thinks it's impossible. All right, well, so what? That's not good enough. There's this notion of a problem being NP complete. And that's what we can use to get a handle on showing something's hard. Intuitively, here's what it means for a problem to be NP complete. It doesn't mean, boss, I know this can't be done, I've proved it. It means, boss, I can't do this, but anybody who's worked on any of these other 900 famous open problems can't do this either. Right? It's not just saying that the few people who have worked on this problem can't do it. It's saying I've connected my problem to show that it is at least as hard as thousands of other problems that also remain exponential at best. So your boss has got to listen to that and say, okay, you know, that's half the world who's worked on those problems, and they've never made any progress, so I guess you probably won't either. Intuitively, that's what it means for a problem to be NP complete. It means it's at least as hard as all these other problems that nobody knows anything better than an exponential algorithm for. Now I'm going to give you a little more specifics on that intuition, but carry that intuition with you because it'll help.
So the difference between an NP and an NP complete is only that the NP complete has been shown to be equivalent to these other problems?
Equivalent or worse? Well, actually equivalent, yes. Yeah, so let me tell you what that means. I didn't tell you what NP is at all, but I'll tell you in a second. Yeah.
In this case, I mean, there's no reason to check all of them, right? Because you've got them handed together, and so if you can satisfy that X and not Y and not Z doesn't work, then you can rule out all the other, those 4 possibilities all at once.
There's a lot of things like that you can try to do, but none of them work in general to get the algorithm's complexity down. You're right, Seth, you're right. And in this particular example, there's lots of particular things you can notice. And there may be, and this is really maybe what you're getting at, maybe there's special cases of this problem that you could solve fast. Right? Maybe the general case is tough, but a special case might be easier. Right? Okay? Well, I gave you a very specific case here where there's 3 in every single, we call these clauses, 3 variables in every single clause. The general problem actually has an unlimited number of variables in each clause. Maybe if there's 3 in each clause, it's easy. Maybe it's simpler. Maybe it's not.
If you're ANDing them together, you rule out a lot.
Well, you're always ANDing them together. That's how it's given to you. So that's okay. You get that for free. All right, before I explain to you this reduction, I want to explain to you a little bit about what an NP complete problem is. Here's the universe of problems. Every little dot is a star in the universe of problems representing a particular problem. Satisfiability is out here. Sorting numbers is in here. P represents the collection of problems that you can solve with a polynomial time algorithm. An n algorithm, an n squared algorithm, an n cubed algorithm. Sorting is n log n. So it's inside here. These are the fast algorithms, the ones we can do on a computer and not have the computer blow up. Algorithms out here, and this is a very particular definition. We'll see this a lot more in algorithms course, but get it here today. NP does not mean not polynomial. It means non-deterministic polynomial. And intuitively, here's what that means. If you have a problem, and somebody gives you a guess at the answer, in this case, the guess would be a particular set of true-false values, a particular 0 and 1 sequence. If you can verify whether that guess works or not in polynomial time, then you've got a non-deterministic polynomial time algorithm. What non-determinism lets you do is do things in parallel when the possibilities are all ORed together. There's 32 possibilities here. I'll have you all work on them, about 32 people here, in parallel. Each of you will do one at a time. If any one of you says yes, it works, then I know the answer is yes. That kind of algorithm is called a non-deterministic algorithm, and it's measured in the time that one of you takes. Not the sum of you take, but one of you. You get to do it in parallel. It speeds up algorithms like crazy. And if you're thinking, well, what kind of ridiculous algorithm is that? You can't do that on a computer. You're right, you can't. They're not practical. They're just a way of thinking about algorithms that seem to speed them up.
And you cannot have the algorithm solved that way? You cannot partition every algorithm?
Well, anything that you can do, anything that's NP is also going to be, anything that's NP could be converted to a polynomial, could be converted to a real-life algorithm, but it would expand like crazy. If I actually calculated how many steps this took, each of you takes just m steps to calculate whether your formula works. But there's 2 to the n of you working. So if I actually turned it into a real-life algorithm, it would explode into the exponential time algorithm we thought of at the beginning. So non-deterministic polynomial means that you get a lot for free. You only have to measure how much time it takes you to handle one guess at the solution.
And that's polynomial time.
If that's polynomial time, the time it takes to guess to check one guess, then we say it's an NP. So almost any algorithm you can think of ends up being NP. There are some that aren't even NP, but it's kind of easy to come up with an NP algorithm. Okay, I'll give you an example. The traveling salesman problem. You have a graph and distances between cities. You want to go through all the cities and get the minimum distance. Okay, so you want to check whether that number, say, is less than some particular value, say less than 1,000. I can just give you a list of cities. You run along the cities, adding up the numbers. You check if it's less than 1,000. You're done. But if I want to check the real minimum, I've got to do this a lot of times, an exponential number of times. Non-determinism says you can avoid doing it all those times. Just do it once and count how many steps it takes to do it once. Yeah.
Well, the traveling salesman problem, finding the minimum, that if you guessed and you figured it out, you wouldn't know if it's the minimum.
The way you normally propose the traveling, it's a good question, Chris. The way you normally present the traveling salesman problem is with a graph, edges on the graph, and a number. And the question is, can you get a path less than that number? Okay. So you have to be able to take every problem and turn it to a yes or no. It's a very good question, but it's a technicality I kind of want to just answer quick and move on. Right. So there's a lot of algorithms out here in NP, and we don't know if they can go down here in the inner universe, like satisfiability. An NP complete problem is a problem that all the other problems in NP reduce to it. Okay, that means it's harder, or at least as hard, as all the other problems. So if you could take satisfiability and find out that it was really inside here, if you took your blue elephant and put it in here, it would pull the pink elephant in with it. There are hundreds and thousands of problems out here that nobody knows how to get them in here. They're big open questions. If you can show that one of those problems is NP complete, then if you were able to get it inside here, then all the other problems would come in with it. Right? And that's the power of showing something's NP complete. It shows you that it's really unlikely you're ever going to get something good. All right, so now I need to show you what a reduction is. Seth asked the question whether it's easier to do this one, because it's ANDed together, or maybe because there's 3 variables in one clause. And then I entertained the question, is it easier because there's only 3 in every one? The general problem has many possible variables in each one. I'm going to convince you right now that having 3 in every one is no easier. And I'm going to do it by reducing the general problem to one where there's only 3 in every single one. And what I mean by that is this. You have a general problem of satisfiability, as many variables as you want per clause. Doesn't matter how long they are. I'm going to show you how to transform that problem into one where there's 3 for every clause. And the answer to my transform problem is going to be the same as the answer to your problem.
Are there 3 clauses in both cases? Or
is in the original, there can be as there can be as many clauses as you want. In the 3 variables per clause.
Well, in the original, there can be as many clauses and as many variables.
And as many variables. And in my transform version, there will be 3 variables per clause and as many clauses as I want.
the general version, does every clause have the same number of variables?
No. Different numbers. Different numbers, right. And I'm going to convince you that having those different numbers is not what makes the problem hard. I'm going to show you that I could very easily take any of these general instances of this problem, convert it to one that looks just like this, and then the answer to this would be the same as the answer to the original. Therefore, what if I came up with a fast algorithm for this 3-variable one? What if Seth went home and said, hey, I got one, and he came in tomorrow? Then what could I do? I could solve the general one. I take my general one, I do this quick little reduction to this kind of case, and I throw it into Seth's algorithm. And Seth would have solved satisfiability. And since we know satisfiability is NP complete, the chance of Seth going home and solving the 3-variable one is pretty unlikely. All right? Not because he's Seth. Seth has a chance after. But he gets 10 extra points, yeah. So I need to convince you I can do this reduction. Everyone understand what I'm trying to do? By the way, if this reduction turned out to be exponential time, if the transformation was a long process, then it's not worth squat. Right? Because if I took a long process of transforming the hard problem to this problem, and Seth came up with an easy solution to this, I still don't have an easy solution for my original, because I've got an exponential blow up in the transformation. So to do a reduction right, you have to make sure that the reduction is done in a time which is negligible relative to what you're trying to prove is impossible. In other words, the reduction should be done in polynomial time. It should be an easy reduction, a simple change, not a complicated one. Yeah?
I believe that it still can be NP complete no matter how many terms that you have. But
Oh, good, because then I'll show you in 5 minutes that if there's 2 terms, you can do it in polynomial time.
okay, that's what I was going to say. I mean, it seems like it would get a lot easier.
3 is hard, and 2 is easy. And this is what theoreticians do. They nail every problem down, they rip it apart, they take every single parameter they can, they go right down to the border, figure out which cases are hard, which cases are easy. So that people who actually have to do engineering know, don't work on this, but this you can do. So in the case of this problem, how many variables per clause is a great parameter to focus on. If there's 2 variables per clause, you can do it fast. If there's 3 variables or more per clause, you're dead. All right? There's other kinds of special cases for problems. For graph problems, you can talk about planar graphs. You can talk about trees. A lot of times the problems are easier on trees. That means there's no cycles. So these are all kinds of special parameters you can look at. But let's go ahead. Let's do this reduction now. Right? So here, if I have a general satisfiability instance, there can be 1 variable in it, or 2 variables, or 3 variables, or 4 variables, or more. Okay? I'm going to show you how to transform any instance step by step into one that has 3 in every spot. So the easiest thing is that if it has 3 variables, just copy it over. Woo-hoo, that's easy. What if it has 1 variable? Say it has the variable x. I have to show you how to transform this x. Here's how I transform it. X plus a plus b, x plus a bar plus b, x plus a plus b bar, x plus a bar plus b bar, where all of these are multiplied by one another. I could ask you on an exam, if I felt like it, that this formula is true if and only if this formula is true. How would you prove that? Give me a method how you'd prove that. How would you prove that this is going to be true if and only if that's true? You could do a truth table. Right? Not so bad. There'd be 8 rows here, 1 row here. If x is true, then for sure these are all true, right? If x is false, is there any way to get all of these true? If x is false, notice I have every combination of a and b. One of them is going to be false, false. No matter what the values of true and false are for a, b. If I have every combination of them, one of them is going to be false, false. That false, false will connect with the false x, and it'll make the whole formula here false because these are all ANDed together. That's my quick proof. But you can do it either in English, like I just did. You can do it in a truth table. These two are equivalent. And that's my transformation for a single variable into things with 3.
The right side to x, like.
Can I go backwards?
Mechanically,
algebraically, and then
do Boolean algebra.
Oh, you can definitely do Boolean algebra and distribute this all out and get x. Absolutely. You could do that. You could do it. Good question. EJ.
Is there something wrong with saying x is equivalent to x plus x plus x?
No, there's nothing wrong with saying that. That's perfectly fine. There's even a law that says you can repeat. Yeah, that's fine.
So how about, why do we do this again?
We're doing this because I want to show you how to take a general formula and turn it into one that has 3 variables for every clause. And I'm starting by dealing with the ones that have 1 per clause. And now I'm going to do the ones that have 2 per clause. Say y and z.
4 clauses now, right?
What?
That has 4 clauses.
This would have 4 clauses, right. I'm going to increase the number of clauses, but only by a constant factor. You know, maybe a multiple of 4 or 6 or something.
You can't do it unless it's 4 clauses.
I don't know any way to do it. No, I don't think you can. How do we convert y and z? Same idea. Maybe someone can think of it. I'll give you a hint. There's only 2 clauses that we need here. Is that a the same as this a? No, it's got to be a different variable. So let's call it c. Good idea, Seth. Same idea here. If y or z is true, then both of these are going to be true. But if y or z is false, then one of them has to be false. Right? Does this work or not? What do you think? Yeah. You can prove it. It's okay. Questions? If they're both false, then one of these will have to be false too, so you'll get all 3 false. All right, now if I have 3, you know I just copy it. That's the easy part. So now I have to deal with 4, 5, 6, 7, 8. And I'm going to do this in general. I'm going to do it with an example of 5, but my example will be completely general. And you can convert anything that was bigger than 3 with this example. So I'll do an example with 5. U plus V plus W plus X plus Y plus Z. Oh, I take it back. I'm doing it with 6. How do we convert something with a lot of things? Here is an idea that's going to build into the last application that I won't have time to do today. Here's an idea that builds in on theorem proving. We start by copying the first 2, and then we have a linking variable, something new called D. We continue with the inverse of that linking variable. We add on the next variable W, and we add a new linking variable. Okay? What would the next term be, just following the pattern? Not E, good. X, F. Then not F. You can just, when you got 2 left, you can just throw them in. D, E, F are all new linking variables. If you do this, you can also prove that these 4 are equivalent to this statement. By an English argument, by truth tables, by manipulation of it algebraically, you can do it. You can prove these. So now I've given you a method that takes any combination of these and creates a new combination of these. If there's a true and false assignment that makes this true, it's also going to make this true because each of these are if and only if. And vice versa. If there's a true and false assignment that makes this true, it'll make this true. So these problems are identical. If I solve this one, I've got a solution for my original. And this is a reduction that takes how much time? You could write a program to do this. What doesn't take so much time? It takes time proportional to the number of variables in the clauses total. You just run along. You just cutter down these lists. It's not so long to do this. It's not exponential time. It's polynomial time. I just look at every variable once. But now I know that Seth's not going to come in tomorrow and give me a solution for this kind of problem, because if he did, I'd have had a solution for the original. And I know somebody proved in the early 70s that the original is NP complete, that every problem in NP reduces to it. Nobody's going to get an algorithm for the original. I should say that if you go look at Slashdot now, there is some guy that's got an algorithm for an NP complete problem that he thinks might run in polynomial time. And there's all sorts of hype about it, because that would imply that P and NP are the same. But nobody thinks they're the same. And there's almost certainly a flaw in the person's paper. The question is, how subtle is the flaw? And when the flaw is found, whether there's anything left to the paper, whether there's still something interesting there. And if there is, then it's still worthwhile. And if it's just the crank kind of a thing, then move on to something else. But I would wager a lot of money that it doesn't really work. Okay, questions about this? All right, so we know this is hard, that satisfiability with 3 variables per clause is now hard. We showed that regular satisfiability reduces to 3 satisfiability. And I love this symbol because it reminds you what it means. It means regular satisfiability is no harder, is less than or equal to 3 satisfiability. 3 satisfiability is just as hard. If you can solve this, you can solve this. So reducing goes in this direction. We started with this one, we reduced to that one. Less than or equal sign in between. Yes?
Just semantics about the notation. It seems like the regular SAT should be slightly harder because we do have that conversion. So I don't see how we can say there's less than or equal to.
Well, it's actually the equal to that lets us say that. The fact is that they're really equivalent because you can reduce it in the other direction too. So they're equivalent for the purposes of whether their polynomial time algorithms exist. They're not equivalent for the purposes of the details of the concept. So you're right, Doug. I mean, if you actually measured, this obviously seems harder than this, right? I mean, it's a tougher problem. But as far as polynomial time algorithms go, this is as hard or worse. Right? It's a good point you raised. All right, so if you have a really hard problem and you reduce it to another problem, what happens to that problem? Is it hard or easy? If you take a hard problem and you reduce it to a new problem, that's also hard, right? How do I show that a problem's easy? I got to do it in the backwards way. If I took 3sat and I reduced it to something like sorting, right? Then it would show 3sat was easy. So if you want to show a problem's easy, then you have to reduce it to something that you know is easy. If you want to show a problem is hard, you have to find a problem that's hard and reduce that problem to your problem. You can use reductions in both directions, depending on whether you want to show something's hard or easy. If you want to show this is hard, reduce a hard problem to it. If you want to show something's easy, reduce it to something else that you know is easy.
Or reduce something that's easy to it, right? Doesn't that technically show that it's easier than that problem?
No, if you did something easy to it wouldn't show anything.
It's not a reduction.
No, that's a reduction. If you reduced in fact, I can reduce 2 satisfiability to satisfiability. I can do that. It's a trivial reduction. Don't do anything to it, right? But that doesn't say anything. This could still be an easy problem, okay? But I'm going to reduce 2 satisfiability to another problem, to basically finding, you might remember this from 2 months ago, finding strongly connected components in a graph. Sometime 2 months ago, when we were doing linear algebra, I tried to connect matrices to the idea of a graph. And remember, we took a matrix and multiplied by itself a lot of times, and I said this gives you the strongly connected components. Those were the pieces where every vertex could connect to every other one. So these 3, they could connect to one another, and these 4 could connect to one another. And you want to divide the graph into its strongly connected components. And we did an algorithm, and it turned out to be not so efficient, like n cubed or something. And I mentioned at the time that there's a really cool algorithm that you'll learn in the algorithms course that does this in time proportional to the number of edges in the graph. A very fast algorithm that uses a technique called depth-first search. It's a really cool algorithm. It is not obvious at all how it works. I will not explain to you the actual details of the algorithm, but I will tell you that it exists, that you'll see it in algorithms. And what I'm going to do today in the next 10 minutes is show you how to take 2 satisfiability, turn it into a graph, so that if I could find the strongly connected components in that graph, I could solve 2 satisfiability. I'm going to reduce 2 satisfiability to this graph problem, which you have to take my word for it now, we can really solve very efficiently. Okay?
And even the inefficient algorithm that we talked about.
Even the inefficient algorithm is polynomial anyway. Right, Chris. Everybody got my plan? I think this is enough of an example. Here's a 2 satisfiability instance, a particular example of a 2 satisfiability problem. Just before we do the reduction, what's the answer to this, by the way? You can probably just do it in your head. Can you satisfy this or not? Well, if x is true, it makes these 2 true.
Why not is true.
And then if y is false, so y not is true, you get these 2 true. So you can do it. Right? I can make x true. But that's okay, but these are ors.
okay.
Right, so actually there's a lot of flexibility. I can solve this. The answer is yes to this question. But that's not what we're interested in. We're interested in transforming it to another problem where the answer to that other problem implies the answer to this problem. I'm just pointing out that the answer happens to be yes, but we do not need to know that in doing a reduction. In fact, in general, when you're doing these reductions from satisfiability to 3 satisfy, you better not know the answer when you're doing the reduction. The answer is hard to do. The reduction's easy to do. You shouldn't have to figure out the answer in doing your reduction. You want to do the reduction completely oblivious to the answer. That's the whole idea of a reduction. You want to connect one problem to another. So I want you to focus on that connection and not the fact that you happen to be able to solve this particular one. All right, so what is a connection going to look like? Here's what we're going to do. I'm going to make a graph where the vertices are going to be the variables here. I'm going to have a vertex for every variable and a vertex for every not of every variable. So here I'll make a picture of that. Here's x, here's x bar, here's y bar, here's, what else? I don't have z. What do I got? W and v. Is that it? I have 4?
X bar are different variables?
X and x bar are different variables, yes. Sorry?
Do you have a straight y or just a y bar?
Oh, I don't have a straight y, but I'm going to include y in there anyway. And it might just end up being disconnected. So if it does, it won't matter. Okay, so that's the first step. Again, imagine you wrote a computer to do this. No big deal, right? Just look at the variables, count them off, create little circles. You got a set of vertices now. Now, how do you make the edges? Here's the tricky part. And I'm not really motivating this. I'm giving you the answer. I mean, to motivate it, I need more than these 10 minutes. So I'm just going to show you how to do it. Here's what you do. For every one of these clauses, say x, y bar, you're going to make 2 edges in the graph. You're going to take the not of the first one and make a directed edge to the second one. So you're going to take not x and make a directed edge to the second one, to not y. Okay? And now vice versa. You're going to take not of the second one and make a directed edge to the first one. So that would make a directed edge from y to x. Okay. That's the mechanical procedure. There is a reason behind this. I'll try to get to it in a minute, but let's just get the mechanical procedure down. I'll try to motivate how anybody thinks of these things. When you first see reductions, your first sense is, God, I'm busting my head just to figure out how this works. Figuring it out from scratch on my own just seems impossible. And, well, it is impossible for the first few times. But if you get led up to it bit by bit, it gets easier. And the good news is that you're not going to do reductions in discrete math. You're going to do reductions in algorithms. So you got a few months to worry about this.
So you did it backwards also? You did also not
You
the second
forward and backwards. Knotting one variable, making an arrow to the other. You got it, Chris? Perfect? Okay. So tell me how to do this one.
It's going to be not v to x.
Not v to x.
And not x to v.
And not x to v. Good. Who wants to do the next one? Sham, can you do the next one? You get the idea? You want to take not of one variable and make an arrow to the other variable.
Oh, okay.
So what do I get?
Not w to y.
Not w to not y.
Not y.
And then
Y to not w.
y to w. You not one variable and you make an arrow to the other variable. So not of this variable gives you y, and an arrow to the other variable gives you y goes to w. Okay. Who wants to do the last one? Who's got it? Erica?
X to not y and y to not x.
X to not y, good. And y to not x, good. Wow. Okay, there it is. There's my graph. All right, so Tony, did I need to have the y in there? Even though it didn't appear in any of the clauses? I needed to have it still, right? Because it connects up to the graph. Right. So, but now you can see that clearly, I think. All right. If you get a variable and you see it repeat again with a not, the answer is You cannot satisfy this. If you don't get anything repeated in any strongly connected component, the answer is you can satisfy it. Now, before we check this, since we know this is satisfiable, this better not have any x and x bar or y and y bar in any connected component. And I don't think it has.
It has a y and y bar.
In the same connected component? I don't think so.
Y goes to x and x goes to y bar.
Where? Y goes... Yes, but y bar can't get back to y. So that's not the same strongly connected component. A strongly connected component is a piece where everything can get to one another. Okay?
So could you give an example of what a strongly connected component going to a variable and its negation would be?
Oh, there isn't one here, but what if it looked like this? If there was a strongly connected component in the graph like this, then the answer would be no, you can't do it. Okay. Let me try to convince you for 2 minutes why this makes sense. This reduction really does work. It's true. And it proves that 2SAT is easy, as long as you know that this is true from algorithms. All of computer science is one big braided bundly thing. You got to know everything. And then, how do you know that this connection works? Well, here's the idea.
Every set of parentheses has to be yes if it's to be yes. So that if the first part is no, the second has to be yes.
Good. So, good idea. If x is true, do you know anything about this? Could be anything. If x is false, what do you know about y bar? Y bar has got to be true. If you have any chance to solve it, y bar has got to be true. But if y bar has got to be true, then look at all the things with y bar in them.
No,
all the things with y in them. Because that would be making the true into a false. The idea is you want to follow these implications through. And when there's only 2 things in each clause, these implications end up giving you a graph. Let me show you. If x is false, what does that imply about y bar? The fact that y bar is true, does that imply anything about any of the other clauses? Not a darn thing. There's no arrows coming out of y bar. Because y doesn't appear in any of the other clauses.
But why doesn't it say something about, for instance...
For this one? Yeah. Because y bar being true doesn't tell you anything about w. You'd have to have y being true, y being false to tell you something about w. Okay? So let's go on to a different example. What about if v is false? Then x has to be true. So let's do it. V is false. Sorry, v is false. That means v bar is true. X is true. If x is true, that means y bar is false. What these arrows represent is a chain of implications of if this is true, then this guy has to be a certain way. And if this is true, then this guy's got to be a certain way. So if you get a cycle where x goes in a long chain of reasoning back to x bar, that means if x bar is true, then x is true. And if x is true, x bar is true. And that can't be. So that's a contradiction. So the answer is you cannot solve the 2SAT formula if any strongly connected component has an x and an x bar in it. You can otherwise. And how do you do it otherwise? You just start here, pick a true or false, and you'll dead end without getting a contradiction. And you can just arrange the true and falses as you go. And if I had a little more time, I know I could get this into everybody's head and make sure you get it. But I really rushed it. And if you're feeling a little bit overwhelmed with it, it's understandable. This reduction is not obvious, but study it for a little bit to get a good sense of a reduction. It's a great example of a reduction. All right, I'm going to quit now. I still have to do the resolution automatic theorem proving thing application next time, and then we'll move on to sets and other topics.